So today, we're diving into a really clever paper. It's about how researchers took one of AI's most powerful and, let's be honest, power-hungry models and taught it to perform at a world-class level, but without needing a supercomputer to do it. This is basically the underdog story of the data-efficient transformer.
And really, this is the central question, isn't it? For the longest time, it felt like the best AI for understanding images was reserved for these huge tech companies with just unbelievable resources. Well, this paper we're talking about, DEET, that stands for Data Efficient Image Transformers, it found a way to completely level the playing field.
Okay, so to really get why this was such a breakthrough, you first got to know the main players. In the world of AI that sees and understands images, there have been these two major families of models, and they've been battling it out for the top spot for a while. On one side, you've got your convolutional neural networks, or ConvNets. These guys have been the undisputed champs for years, right? They were literally designed for image tasks and are super optimized. And on the other side, you've got this incredibly powerful challenger, the Transformer. These are the models that totally took over the world of language AI, and then they set their sights on computer vision. But here's the thing about this powerful new challenger. It had a bit of an Achilles heel, a really fundamental weakness that was holding it back from being something that, everyone could use. So, the first big success story here was a model called the Vision Transformer, or VIT, and it was a huge deal. It proved that a pure transformer could go toe-to-toe with the best ConvNets. But it came with a massive catch. And it wasn't a secret. The original paper just laid it out there in black and white. Transformers are fantastic, but they don't learn very well if you don't feed them an absolutely insane amount of data. They were powerful, for sure, but they were fundamentally data-hungry. And how much data are we talking about here? Well, the original Vision Transformer was trained on a private Google dataset that had 300 million images. I mean, think about that. That's a resource that almost nobody else on the planet has access to. So for most researchers, this amazing new technology was pretty much a non-starter. So, how did the Datite researchers get around this huge problem? Well, they didn't go out and find some new, even bigger dataset. No. Instead, they used this really clever training strategy where the new model essentially learns from an older, wiser expert. This whole technique is called knowledge distillation. And you can think of it like this. Imagine a student model that's trying to learn. It doesn't just study from a textbook to get the right answers. It also gets to watch a brilliant teacher model solve the same problems. And in doing so, it learns the teacher's thought process, its intuition, all those little nuances. So the whole point of this was to take all the wisdom that an expert model had already learned and figure out how to efficiently transfer it to a brand new transformer. And if they could pull it off, it meant the new model could learn from a much smaller, standard dataset, like ImageNet. But here's where it gets really interesting. The DD researchers didn't just use some off-the-shelf distillation method. Nope. They invented a totally new approach that was perfectly designed for the transformer architecture, and it all boils down to one special secret ingredient. And this diagram just shows their ideas so well. See, in a normal vision transformer, you feed it pieces of an image, we call them patches, and you add a special class token that learns to make the final prediction. What the DATE team did was add a second special token, which they called the distillation token. Okay, let's break this down, because this is the key. The model is now juggling three different kinds of information. First, you have the patch tokens. That's just the image itself broken into little squares. Then you have the class token. Its job is to learn the actual correct answer from the dataset. And finally, you have this new distillation token, and its only job is to learn how to perfectly copy whatever the teacher model predicts. And this is just so smart. The model is forced to learn from two different sources of truth at the exact same time. It has to figure out the right answer from the data, but it also has to absorb all the patterns and biases that the expert teacher model has already learned. So the theory is fantastic, right? But does it actually work in practice? Well, the researchers put their new data-efficient transformer, DEET, to the ultimate test against the reigning champions of the day. This chart just tells the whole story so clearly. Okay, look at the blue dots way down at the bottom. That's the original VIT model trained only on ImageNet. It does terribly, just like the paper said it would. Now, that yellow line, that represents EfficientNet, a top-of-the-line ConvNet champion. And the red dots, well, that's DAIT. It doesn't just catch up to the champion, it blows right past it, all while training on the exact same, much smaller dataset. And the raw numbers here just confirm what we saw in the chart. Look at this. The DIT model trained only on the standard ImageNet dataset
hits 85.2% accuracy, beating out the top ConvetNet. And what's maybe even more impressive is its throughput. It's nearly twice as fast. So it's not just more accurate, it's also way more efficient.
So what's the big picture here? Why does this matter so much? Well, this isn't just a story about one faster and better model. This breakthrough had really broad implications for the entire field of AI.
It really boils down to three things. First, accessibility. Suddenly, these state-of-the-art transformers weren't locked away inside corporate data centers anymore. Second, efficiency. I mean, being able to train one of these on a single machine in just 2 or 3 days, that's a huge leap. And what that means together is that innovation can now happen anywhere, completely leveling the playing field for researchers all over the world.
And here is a final, just fascinating little detail from the paper. They found that the absolute best teacher for a new transformer student wasn't another, bigger transformer. It was actually a ConvNet, the old champion. It's kind of poetic, right? The best way forward was for the new challenger to learn from the wisdom of the old king. So that leaves us with this really interesting question. For so long, the biggest thing holding transformers back was this massive need for data and computing power. Now that that barrier has been smashed, what's next? What new discoveries and applications are going to be unlocked now that everyone can get their hands on this tech?